Hi, and welcome to the fourth episode of Basha's Thoughts. Since the last episode, I have gotten a few questions, and most of them seem to be related to science, physics, and so I thought maybe we could focus on that in this episode, on explaining some of the quantum experiments that I mentioned but didn't really go into in the last episode, so that it can become easier to grasp what it is we're talking about. Before I go into the experiments themselves, I thought it would be good to just quickly reiterate what it actually was we were talking about in the last episode. And that had to do with reality. What is real? And we looked at the science part, and we looked at a more personal part, practical part, how we experience things, as well as some spirituality. When it comes to science, I was suggesting that maybe it is time to move away from materialism. And that way, science, especially physics, could become much more useful and go much deeper than it is going at this time. And maybe at that point, we could find some type of ontology showing us what is real. And I was basing this on some experiments that we have had lately. I was basing it on the quantum theory, and in particular, I think I mentioned two experiments that have recently been done physically. Before that, they were actually just thought experiments. And these seem to indicate that maybe, perhaps, there is no material universe out there. Maybe there is no objective, observer-independent material world for us to interact with. So let's start with Wheeler's delayed choice experiment and then move on to Wigner's friend experiment. To understand the delayed choice experiment, it is good to know a little bit more about the double slit experiment. So, in quantum mechanics, a state is described by a wave function. And this may initially sound really strange. Why would you use a wave function to describe something? So I want to talk about this. To start with, let's start with something really physical, really tangible. So let's imagine a wall, and it has two really tall windows, one next to each other. They are very narrow and tall, so like two slits in a wall. And you have a bunch of, let's say, balls that have just been painted, and you're throwing the balls at the wall. And some of the balls go through the windows. And on the other side, a few meters behind it, there's another wall, a white wall. And as you throw your ball, if it passes through one of the windows, it will continue onto the other wall. And as it hits the other wall, you will see exactly where it hit, because it will leave a red mark. And so there you are. You're standing and you're just throwing the balls in the direction of the wall and of the two slits. After some time, you will notice that on the wall behind the wall with the two windows, you will start to be getting a pattern of where the balls hit. And it will be something that is kind of a little bit similar to the two slits that they went through, like two lines where they hit. Not exactly lines, they're not all that narrow, but two, you could still say two lines. Okay, that's pretty normal. Now imagine that you fill this area with water, and the water can flow through the two slits. Now if you start to generate waves, flat waves, kind of like the ones in the ocean, and so you generate a wave. There's a wave top, and then there's the bottom, and there's a top, and there's the bottom. What will happen as these waves approach the slits? Well, some of the water will go through the slits, and as it does so, on the other side, you will see that you no longer have straight waves. They will be like half circles moving away from each of the holes. You can imagine that. And the thing is that as they move away, further and further away, whenever a wave top from one of the holes meets another wave top, that wave top will be even higher. And where a top meets a bottom, there will be nothing, no wave, right? So you will get a type of interference pattern based on these waves interfering with each other, interacting with each other. And now, if you go to the wall that is behind and you look at where the intensity of the waves that hit the most is, where do the waves hit the strongest? Where do they reach the highest? You will actually see that this happens exactly in the middle between the two slits. So now you have a lot of waves hitting in the middle, and then you have like little, you could say little lines moving away with less and less intensity. And this we call an interference pattern. So you can see that waves can create interference patterns, but little balls, tennis balls that have been painted, do not create these interference patterns behind the double slit wall. Okay, this is all reasonable. Now, what happens if we, instead of throwing balls, start throwing electrons? So electrons are made out of matter. They have matter. They're tiny, but still. So these are kind of tiny. You could imagine them as tiny balls of matter. Would that be an accurate picture? Well, let us see. So we create the same experiment. Now we start bombarding the wall with the two slits. Now these slits are much, much smaller, of course, because we're making everything in the proportion for the electrons. And we have a detector on the wall where we used to have the paint before. And the detector will tell us exactly where they hit. Now, what do you think happens if we start shooting away a lot of electrons through the double slit? Actually, we will get an interference pattern. Oh, that's strange. So then maybe this electron is not really a particle. Maybe it's more like a wave. And so this is the particle-wave duality. Is it a particle or is it a wave? But why would you think that it's a particle? Well, it has mass. But now you may be thinking, well, so electrons act like waves and they interact and interfere with other electrons. Is that what is happening? Actually, it's even more weird because you can shoot electrons one at a time so that it doesn't have many other electrons to interfere with. What happens then if you just shoot one electron at a time through this double slit? Actually, the same thing happens. It creates an interference pattern. So that would mean that the electron interferes with itself. This particle interferes with itself and creates an interference pattern. And so we tend to have a state of superposition, because if ontologically now you ask, so where is the massive electron? Is it going through the first slit or is it going through the second slit? Well, it seems to be going through both slits. So it seems to be both in the first and the second slit at the same time. And then it seems to be interfering with itself. So here you have a superposition. And this is like something that has been called a potentiality. But this is very real. Indeed, you see a real confirmation of this. You see the interference pattern. And it only happens when the electron can interfere with itself. So what if... Now here's an interesting thought. What if you could check which hole or which slit the electron actually goes through? What if you had a way of checking? And you looked, and you said, okay, it went through the first slit. Now it went through the second slit. All right, you can create an experiment like that. What will happen? Actually, then the particle, the electron, will no longer act as a wave. It will act as a particle, and you will not get the interference pattern on the other side. you will get the two slits just like you got when you were throwing the red tennis balls at the wall. So you will only get that pattern. So you're thinking, okay, but so we're talking about really tiny particles. Maybe the act of measurement somehow, the act of observing the particle and then knowing which way it went, maybe that is what actually creates the pattern. And here we're starting to get to experiments like Wheeler's delayed choice experiment. There are many different thought experiments related to this, and there are also different experimental setups. But let me just give you an example based on the double slit experiment. So now imagine the following. You have the possibility of measuring which slit the electron goes through, but you don't choose to check until it has already passed the slit, but before it has hit the detector, right? So imagine you're kind of checking which slit it's going to, but you will only get that information if you decide that you want to get that information. So it's a choice that you're making. So as the particles go through the slit, you haven't decided anything yet, and then they are on their way to the detector, and then before they hit the detector, you say, okay, I'm going to see where it went through. What happens now? The strange thing is that if you have the ability to get that information, then the particle will act as a particle and not as a wave. And it is not related to the measurement or observation on the other side. Because what you can actually do is you can scramble the information. So you can always be measuring, but then on the way you can decide to scramble the information so that you cannot access it. So the information is there, but not for you to access. And there's no way you can find out which slit it went through. So whenever you can do that, scramble the information so that you don't know, you will get an interference pattern. And whenever you can get that information and know which way it went, well, then you will get no interference pattern. So this has to do with the delayed choice experiment. Now, Wigner's friend, it was just last year, I think in February, that a physical experiment was published and showed that this is actually so. But it was in the 1960s, I think it was in 61, that Eugene Wigner, who was a physicist, came up with this thought experiment. And it's the following. So suppose there is a state that is in superposition. Superposition is kind of like the electron being in two places at the same time. So you can have, for instance, a photon, and it can be in the state of superposition when it comes to polarization. So you can have, let's say, vertical and horizontally polarized at the same time. Now, if you go to measure, you will see that it's only vertical or only horizontal polarization of the photon. It can only have one, but it is actually in the state of having both, as long as you have no access to the information about it and you're not measuring it, right? Which would give you the access to that information. So this is the idea. You have some kind of a physical experiment where you have a physical state in a state of superposition. Now, you also have a friend. So Wigner has a friend. And the friend, she has a laboratory. And this laboratory is totally isolated from everything in the world. So she takes this physical state into the laboratory, and you decide, okay, at a particular time, she's going to measure it, and she will know if it's horizontally or vertically polarized. Great. So let's say noon exactly. She walks in there, it's 11 o'clock, she's setting up her experiment, but you have no contact with her because she's totally isolated inside of the laboratory. Wigner has no contact. And his friend is performing the experiment. Noon comes, and she stays in the laboratory. Now it's 1 o'clock. What is happening now? For Wigner's friend, something has happened. For Wigner's friend, there's either the state of horizontal or vertical that was measured. So there's either one or the other. But for Wigner, what is the state? For Wigner, actually what happens is that the whole laboratory and his friend go into a state of superposition with the two different records. So nothing has happened in that sense, in the sense of a measurement. The measurement has happened for the friend, and there is one objective outcome, she thinks. But for him, all of that is in a state of superposition. Now, this may seem really strange and really not logical in some ways, but this is based on the laws of quantum mechanics. So in the real world, this would not really happen. Why? Well, because you cannot really isolate a laboratory that way. It's just too big. But if you go to the smaller particles, you can actually set up an experiment like this. So in the large sense, you could think, well, no, it's just that Wigner doesn't know what has happened. It's not that there's a state of superposition. There's no state of superposition. He just doesn't have enough information. He's just lacking information. That's what's going on. A lot of people have been saying these kinds of things about quantum theory in the past, especially in the beginning when it was created, because it is probabilistic. And so it's like there's hidden variables, there's information missing, there's something we're missing. So in this sense, also they would say, well, no, Wigner just doesn't know what is going on. And then when the friend comes out, boom, now we have an outcome. Now we know what has happened. There's no longer a state of superposition. But the thing is that what you can actually do when you're doing this experiment is that you can, as Wigner, you can create an interference measurement on the friend and the outcome. Interference measurement, just like we did with the double slit. Because your friend is in a superposition, like with the double slit, when there is a superposition that's going on, the pattern that you get is an interference pattern, which is very different from when there is one particular outcome. Yeah? When there is one particular outcome, when the electron has gone through one particular slit, there is no interference pattern. But when there is a superposition and the electron seems to be going through both slits at the same time, or your friend seems to have gotten both results at the same time, there is a superposition, and there is an interference pattern if you do an interference pattern measurement. And you can do that in physics. So they actually did this experiment. Well, they did it in a slightly more complex way because they actually used 4 observers, you could say. Here we only have 2, Wigner and the friend. And they often tend to enjoy using Alice and Bob. So here again we have Alice and Bob and Alice's friend and Bob's friend. And they were using photons, and they were using the polarization of them. And indeed, what you find is that depending on the observer, at noon, for instance, one observer tells you, this is the objective outcome of a measurement. This is the measurable physical universe out there. This is what is going on. While another observer, Wigner, will tell you, no. Now, at noon, what is actually going on is a superposition. I have the physical experiment here, and I have your pattern that shows you that this is what's going on. So, which is right? So what actually happened at noon? Was there an outcome or wasn't there an outcome? What is this objective physical world out there that we are measuring? See, that's the idea. The idea is that these types of experiment kind of put into question the independence of observers. There is no observer-independent universe out there. We already tweaked this a little bit with relativity, with Einstein's theory of relativity, because before that we thought that there was one unique objective observer. But then we realized, no, the observer is actually dependent on the moving frame of reference. So what is going on will depend on the frame of reference. Okay. But still, there is something going on. You just have different points of view, you could say, but still everything is deterministic. Now, determinism is out, and the observer independence doesn't seem to hold anymore. This objective universe only seems to come into place whenever we have a particular perspective, whenever there is a clear experimental setup established. Superpositions seem to give us the idea that something can exist in different places at the same time, whereas the delayed choice experiment sort of shows us that different pasts can kind of coexist, and it's only when you make the choice that you choose a past. It is only in the present moment when you choose that you decide on what was the past, right? So if you look at the delayed choice experiment where you have the double slit, and it's only after it has passed through the slit that you decide, okay, I'm going to check what happened in the past, if it went through a slit or didn't. So your decision there will will look like it's influencing the past, because now you decide that it would have gone through one or the other slit. Whereas if you say, no, I'm not going to check that, well, then it will have gone through both and you get an interference pattern. And so here you have as if a superposition in time, whereas otherwise you have a superposition in space or in state. And so just finishing up, we see that there are some things in quantum mechanics that seem to indicate that maybe moving away from materialism and the supposition that there is a material world out there, independent of consciousness, that is objectively existing, perhaps is an interesting choice. And if we look at what is real, the outcomes of measurements are only projections, are only small, tiny parts of what is actually happening. I hope this clarified at least the quantum examples, and I look forward to seeing you in the next episode. Take care.